which is called joints. Okay. Now, some people call it connection design, but the actual term in Euro Code 3 is actually joints lah. So joints, there can be several types of joints in steel, okay, as you will see later. So obviously steel members, steel members are manufactured in factories and then they transport it to site. That means because you need to transport it to site, it has to fit onto a lorry. So anything too big or too long will have to be cut up, okay, so it can fit onto the lorry to be sent to site. That's why you end up introducing joints in your steel members. All right. So for example, a column for a let's say 5-story building. One story is about 4 meters. So if you have a column for a 5-story building, that means the column altogether is 20 meters long for a 5-story building. Now, 20-meter long column, you cannot transport it to site as is. You have to separate it into a few manageable pieces. So normally lorries can fit up to 12 meters. But even then, 12 meters, you need special permit, all right, to carry anything that long, all right? But generally, we use 12 meters as a guideline. So if you have a 20-meter long beam, then you're gonna have to at least chop that column in half. So you introduce a joint in that column, which you have to connect back once you get to site. Okay, so someone has to design that connection, and you'll be the engineer, who's gonna design the connection. Okay, so that's basically why we have joints in buildings. You also have joints when you connect the beams to the columns, when you connect bracing to the columns and to the beams, and things like trusses, you have lots of joints. Okay, so to understand how joint works, you have to go back to type of columns or type of structures again. All right, so this is a slide from your previous lecture. Okay, so basically there are two types of buildings. You have a braced frame building, you have an unbraced frame building. All right, so in a braced frame building, the joints are typically pinned, whereas in an unbraced frame building, the joints are typically fixed. In other words, or fixed or rigid, or you can call them moment connections. All right, so therefore, pinned and moment connections, they are different. Okay, the requirement is different. Pin connection, you only have to transfer shear, you have to transfer axial force. Moment connections, you have to transfer shear, axial, and also moment. So the moment is the tricky part. Okay, so you got the additional force to deal with, okay, when you're looking at moment connections. So that's why, yeah, there are different requirements. So the type of joints you design would depend on the type of frames, structural frame that you're considering. Okay. Now there are there are generally two ways of forming a connection in a joint. Okay. The first one is using welding, by doing welding. Okay. So obviously when you weld, you can attain quite a good rigid connection. So welding gives you quite a good rigid connection. So most of the time, if you do welded connection, you will get a full moment connection most of the time. Okay. So it gives you something rigid. It can take a lot of loading, but there are challenges, okay, associated with welding. First of all, welding means if you've seen people do welding before, you will see that they carry this big welding machine. Okay, to do welding, you need a welding machine. If let's say you are doing a connection between a beam and a column at 3 stories above ground, you're going to have to carry that machine all the way up there, which is very, very tricky, very, very challenging. Okay, so yes, the welded connection is good, it's strong, but it's difficult to do, especially at height. And you also need skilled labor to do welding. You cannot just simply pick up anyone on site and ask him to do welding. Cannot. Okay. Welders have to be certified because the quality of the weld is very dependent on the workmanship and the skill of the welder. All right. So that's welding. Okay. Good strength and good rigidity, but you need skilled labor to do it. And it's challenging at height. Okay. So that's welding. The second type of connection is bolted connection. So bolted connections means you have a beam. So let's say you are connecting a beam to a column using bolted connection. In this case, the beam will get sent to site with an end plate. So that end plate will get bolted to the face of the column using bolts and nuts. All right. Now, bolted connection normally can take quite a lot of shear, can take quite a lot of axial load, but it has limited moment capacity. All right. So bolted connections have very limited moment capacity. To get, if you let's say you only use 4 bolts or 2 bolts, you definitely get 0. Okay. 2 or 4 bolts, you get 0 moment out of it. If you want it to carry moment, you need to have an arrangement where you have like 8 bolts. Then it has some moment capacity in it. Okay, so you can design bolted connection to carry moment, but not easily lah. All right. So at the bottom of the graphics, you can see basically comparison between the two types of connections. All right. Now, the good thing about bolted connection is you don't need skilled labor for it. Okay. And it's quite simple. You can send someone up, climb up there with a few bolts and a wrench, and he can do the connection easily. So you don't need skilled labor. You don't need big, heavy machinery to do it. Okay. All right. This next slide shows you, okay, all the possible joint locations in a steel building. All right. So this is a screenshot from a book. That's why you if you look through it, you can see pages 10 to 82, tables G1 to G7. It's actually referring to sections in a book because I took this screenshot from a book. All right. But doesn't matter. I've included it here just for your reference. Okay, just so that you can see all the possible places where a joint may occur in a steel building. All right. So, what's the difference between the left and the right hand side? Okay. So on the left, you have an I column, I shape or H. Yeah, H-shaped column with a base plate on the ground. So that base plate is also a connection. So right at the bottom of that column is a base plate. That base plate is needed so that you can fix the column to the concrete foundation. All right. Now, as you go up the column, you will see splices in the column where the column gets chopped in half during transportation. Okay. So when you cut a column in half, when you have to if you have to transport it, you have to connect it back on site. So that's one of the joints that you have to design for. Okay. As you go further up the column, you get beams connected into the column. Let me see if I can draw. Eh, can recognize my face block. All right. So, okay. So, right at the bottom, you have base plate. Okay. So, what the base plate does is it has holes in it to allow you to put a bolt through the hole into the concrete foundation to fix it to the concrete foundation. So that's a connection that you have to design. All right. As you proceed up the column, you can see a connection between the top column and the bottom column, and you have a plate to splice the two columns together. All right. When you go further up, you have this connection here, which is beam to column connection. Now, beam to column connection, there are a few types you can choose from. If you need a simple one, you don't need to carry moment. That's the one you go for. It's called fin plate. Fin plate connection. Okay. So fin plate connection is when you have a plate that's welded to the side of the column, and then you just slot your beam in, and then you put the bolts in, and then connection finish. All right. Now, you can also do fin plate connection if you need to do beam to beam. Okay, I'm going to use another color here. You see here? How come it's still red? uh, there, the blue color, that is a beam to beam connection. Yeah, sometimes you have a beam supporting another beam, so you have to connect the two beams together. All right, so you can also use fin plate connection for that. If you go further up the column, this is another connection where you connect a beam to the side face to the sides of the column. Yeah, to the side of the column. And this is called an end plate connection. Okay. So an end plate connection is more involved. Okay. So end plate connection, you can obviously see the difference between end plate and the fin plate below. End plate connection, you have much more bolts. You have 8 bolts. Fin plate, you only have 3 bolts. Okay. So end plate connection, you can put up to 8 bolts or even more if you want to. Okay. There are ways to do even more. Okay. But in this case, 8 bolts. Okay. So the more bolts you put in, it starts getting more rigid. So you can start carrying moment. So fin plate, you cannot carry moment, but end plate, you can start designing it to carry moment connection. Okay. So that's for a normal I-beam connected to a H column, H section. All right. Now, on the right-hand side, all right, on the right-hand side, you have something similar, but except the column is not an H column. On the right-hand side, the column is this is what's called a square hollow. Okay, square hollow section. It's basically a hollow unit. All right. It can be square, it can be rectangular, but in this case, it's square. It looks square to me. All right. So when you have a square hollow section, then the connection is a little bit varied. Okay. The first thing that you probably notice is the difference is here. Okay, here. When you join the top column and the bottom column together, you cannot use a splice plate anymore. You need to use end plate. Okay. Why? Because if you have a square hollow section, now if you imagine when you install a bolt and a nut, you put the yeah, let me show you somewhere. Okay. Let's say this is a steel plate. I want to connect one steel plate to another steel plate. Okay, so two steel plates together. I want to connect them together. So I have the holes in the steel plate. Okay, so I want to connect the two plates together. Now, to connect the two plates together, you slot a bolt in from one side. So a bolt normally has a head, and then it has the threaded part here. Okay, yeah, so macam ni. A bolt typically looks like that, and it has all the threads here. Okay. Now, so your bolt comes in from one end, and then your nut comes in from the other end. Yeah, the other end you put your nut in. Okay, so you turn the nut tightly so that it forms the connection. Now, the thing with this is you need access from both sides. You need access from the left. You need access from the right to do the to tighten the connection. All right. So that's where the problem with square hollow section is. Square hollow section, you only have access to one side, the outside. You cannot tighten anything from the other side, inside, because you cannot get your hands in there. Yeah. So that's why you use an end plate connection so that you can actually install the nuts. Okay. So that's why there are differences lah. Okay, on how you do connection between the two. All right. But all the others are similar lah. Okay. So so okay. So now I'm gonna very briefly speak about the text on the right. Okay. So when you do connection, as I mentioned earlier, you can do a pinned connect. The simplest one is a pin connection, normally nominally pinned. That means even though it can carry a bit of moment, you assume it doesn't carry any moment. Okay, you just treat it as pin. Okay. Now there's another type of connection where it's rigid and full strength. That means you can use it to carry moment. Okay. Now there's also another type which is semi-rigid. Semi-rigid, which means it's not fully pinned, but it also cannot carry full moment. It's somewhere in between. Okay. So that is semi-rigid. Okay. It's not fully pinned, but it can, but neither can it carry full moment. So it's somewhere in between, between pinned and rigid. Okay. So it's called semi-rigid. All right. All right. Now, next. Next are examples. Next are examples referring to the image, to the graphic, to the graphics on the left-hand side. Okay. So places where connections can occur. So you have beam to column connections. So you can use end plates, partial end plates, full end plates, or fin plates. B, connections, column splices. Column splices where you connect. So column splices means you connect top and bottom column together. Okay. So that's what column splice mean when you have to connect top and bottom column together. All right. So you use bolted splice plate, or you can use end plate. Okay. Now you have column base plate. Column base plate is for you to fix the entire column to the concrete foundation. Okay. Could be a mass concrete footing, could be a pile cap. All right. And lastly, the bracing connections. Obviously, if it's a brace structure, you need to connect the bracing to your steel frame as well. Okay. Okay. Next, we compare the type of uh what's that, beam to column connection. So these are typical connections that you use for beam to column connections. So this is A lah, A, beam to beam and beam to column connections. Okay. So this is just a table summarizing the different choices. All right. So you have your partial, depth, and plate, which can carry a good amount of shear, not full, but it can carry up to a certain amount, normally up to 75%. The tie resistance is average, fair. Okay. And special consideration, you don't have to worry. Okay. Now, fabrication and treatment, it's the same, right? It's all good. Okay. Erection, also the same. Okay. It's all bolted connections. So really, for this table, the only thing that you have to concern yourself with is actually this. The first part. That's really where it makes this is basically where most of the differences come from. Okay, between the three types of plated connections. Okay, so partial end plate, you can carry a decent amount of shear. Full depth end plate, you can carry full shear, up to 100%. The weakest one is thin plate, only up to about 50% shear it can carry. Okay, now the tying resistance, the partial depth end plate, it's average, but full depth end plate and thin plate is good for tying resistance. Okay, this is the only role that is important. Okay, on this slide. Okay. Okay, next. Okay, materials. So we have to, before we do design, we have to speak very briefly about the materials used here. Okay. Now, bolted connections. Now, the bolts used in bolted connections. Apologies, I was reading my WhatsApp just now. Got important message coming in. Okay, now, the bolts that you use in bolted connection, it doesn't come in the same grade as your steel members. So so if you can recall from previous classes, steel grades that are commonly used are grade 275 and 355. Okay, so these are the common grades or common strength used in steelwork design. Okay, now bolts are different. Bolt classes come in this destination. Yeah, so if you refer to the table at the top, you have 4 different bolt classes: 4.6, 5.6, 8.8, 10.9. Okay, so the different bolt classes refers to obviously different yield strength and different ultimate strength. So FYB. FYB is yield. FUB is ultimate strength. Okay, so FYB is yield. FUB is ultimate strength. Okay, so you have four bolt classes that you can choose from. Okay, and they correspond to different yield strengths and ultimate strength. Now, the most common one, the one that you have to concern yourself with is 8.8 only. That's the only one that really that we use. We don't use anything else. The most common one is 8.8. So that's the one that you concern yourself with in this course. Okay. So you just worry about 8.8. Okay. Yang line 2, the rest you don't have to remember. Okay. Now, so that is bolt strength. Bolt strength different from your steel strength. Okay, even though they are made from the same material, but the strength is different. Okay. Now next, you have your steel strength. Now the steel strength is basically strength of your steel beam, your steel column. So this is the same table. So steel strength is at the bottom. This is the strength of your beam, of your column. Okay, those stuff. And this is the same table that I've shown you previously for when we were doing beam and column design. Same table, okay? 275355. So as the plate thickness increases, then the strength reduces. Okay. This one we've gone through before when we were doing beam and column design. Okay. Now next, the checks that you have to do. Let me move this. Can I move? To move. Okay. Make it bigger. Okay. Okay. You see that thing that you see the text box that I made bigger. Okay. So I made it bigger so that I can capture your attention. These are basically, when you do connection design, these are basically the checks that you have to carry out. For this, so basically these are the ways that your connection can fail. So that means you have to check it, okay, to make sure it doesn't fail. All right. So these are the ways that your connection can fail. So you have to check to make sure that it doesn't fail in any of these manners. Okay. The first one is shear failure. All right. The first one is shear failure. The second one is bearing resistance, bearing failure. Okay. The third is tension failure. The fourth is combined shear and tension failure. Now, what is shear failure? All right. Maybe better if I look this. All right. Okay. Shear failure. I will, because I have very limited space to draw, I will draw for you to show you what type of failure it is, but then I have to erase it later. Okay. Now shear failure is when you connect one plate. Wait. Maybe how come this? I don't know. All right. Okay. When you connect two plates, let's say connect two plates together. When you connect two plates together, all right. So you have your bolt holes, and you put a bolt through, and then you lock it with a nut. All right. Now, shear failure means when the force is this way. Okay, when the force is this way, that means the bolt is being sheared. The bolt is being sheared like that. Okay. It tries to break your bolt through shearing. Okay. This is shear failure. All right. What is bearing? Bearing resistance. Okay. Bearing resistance is this one difficult to draw. Let me try. So bearing resistance is, let's say you have a concrete, let's say this is a concrete foundation. You have a column, base plate, and then you have a column on top. So you have a column sitting on your concrete foundation. Okay. Now this column has wait, I use blue. So this column is carrying some axial compression load. I don't know how much, maybe 1,000, let's say. Okay, this column is carrying some axial compression load, 1,000. This 1,000 has to be transferred to the foundation below through the plate, through this plate. So this 1,000 is going to get spread as bearing underneath that plate. Okay. So the stress underneath is 1000 divided by the area. So this plate has an area. This plate, nah, plate, if you think of a plate, it has an area, ma. Yeah. Tinggi, apa? Panjang. Panjang darat lebar. Panjang darat lebar gives you the area. Okay. So your 1000 divided by your panjang darat lebar area gives you some sort of stress there underneath the plate. Now, that stress has to be less than your concrete punya stress lah. Your concrete strength, your concrete strength below. If it's higher than your concrete strength below, the concrete is going to get crushed. Yeah. If the stress is too high, your concrete below will get crushed by your column. So then the way you deal with it is, if that's the case, then this plate bigger, you have to make this plate bigger. The bigger your plate, the bigger the area, ma. Yeah, your plate bigger, that means your area is bigger. So 1000 divided by a bigger area gives you a lower stress. Yeah, so makes sense. Okay, so that's why you have to check whether your plate is big enough or not to spread the load. If it's not big enough to spread the load, you have to make your plate bigger so that it doesn't fail in bearing. Okay, so this is bearing. Okay. Now let me delete this one. Next is tension. Next is tension. So tension, I will use green color. Okay, I use green color for tension. Tension, simple. Tension is if you have a force. The plate at the bottom is getting pulled that side. The plate on the right is getting pulled to the right. The plate on the left is getting pulled to the left. Yeah, the force, opposite direction. What that means is your boat will also get pulled. Your boat will get pulled in both directions. Then your boat goes into tension. Boat in tension because it's getting pulled by the plate. So you have to check, make sure the boat doesn't fail in tension. All right, so that's tension. The last one is combined shear and tension, which is what I've drawn here. So now combined shear and tension is when the blue color occurs at the same time as the green color. Yeah, you have two forces here. I have two forces in my sketch here. Blue is shear, green is tension. When the two occurs at the same time, then you have combined shear and tension. So then you have to check for combined shear and tension. Sometimes it's only shear, sometimes it's only tension, but sometimes you get both together. Then you have to check for combined shear and tension. Okay. Okay, everything good so far? Any questions you want to ask me?
No, all clear.
Everything's clear? Okay. All right, so if everything's clear, I will continue. Okay. So these are examples of bolted connections. Okay, some examples, I stole this from someone's book. All right. I didn't draw them. I stole them from someone's book, but they are very good examples. All right. Now, these are examples of normal connection of types of connections. All right. Now, on the left hand side, I'm going to use the same color coding. Wait. Wait. Okay. I'm going to use the same color coding. Blue is shear. Okay. So on your left hand side, it's basically, hey, how come it's green? On the left hand side, it's shear. So all this is shear. Examples of shear connection. Okay, whenever you see something like this, that means it's shear connection. Yeah, shear connection is, if you look like what I explained, you have your bolt, and then your force is this way. Your force is perpendicular, like you can say. Your force is perpendicular to the bolt. Yeah. When your force is perpendicular to your bolt, that's when you have shear. Yeah. Force perpendicular to the bolt. Yeah. You look at this one. Another bolt. The force is perpendicular to the bolt. Shear. All right. So whenever you see examples, because in test and exam, I'll give you something like this. I'll give you a gambar raja like this, and then I will ask you to design. So you can tengok. You need to know exactly what sort of, whether it's shear or whether it's tension. Okay, I will just give you a screenshot, a picture of this. Then I ask you to do the design. You need to know whether it's going to be shear or tension. That's why I give you all these examples. All right. Now, the one on the right is where you have combined shear and tension together. Okay, so if you look at, for example, let's look at this one here. Hey, I want to ask you, when I zoom in, can you see me zooming in, or you don't see the size changing? When I zoom in, right now, actually, I'm zoomed into one of the view.
Yes, we
Can you
can
see
see
it?
it, doctor.
You can see me zoom in?
Yes.
Okay, that's good. Okay. All right, so I zoom into one of the connections here. Okay, so this is, for this connection, you have column here. Okay, you have column on the left, and then you have some sort of corbel. This is a corbel, like a, it's like a, so this is a corbel. A corbel is like a short cantilever. Why is it doing that? Yeah, a corbel. That's a corbel. A corbel is like a short cantilever. All right, I'm not gonna try to write on it. Okay, now what it's doing is it's carrying a force. That corbel is carrying a force here. It's carrying a force here. That force has to be transferred to the column. So that P, that force P, somehow has to make its way into the column through the connection. Okay, it has to make its way through the corbel, in through the connection into the column. Okay, so the way that works is through the connection. So you look at that corbel. All right, you look at a corbel. So that force P will become shear in that connection there. Okay, will become shear in that connection there. Okay, but because it's a cantilever, then there will be some moments involved. Now that P is a distance E from the face of the column. So because because it's at a distance E, what happens then is it causes a moment. It causes a moment in the connection. So when it causes a moment in the connection, then your 1, 2, 3, 4, your 4 sets of bolts here will start going into tension. The top one will go into tension. The bottom one will go into compression. Okay? Why? Because you imagine your column. Yeah. You imagine your column and the corbel is like that. Okay, and I put a force here. So that corbel wants to rotate. When it rotates, When it rotates, the entire cover wants to move. Yeah. Okay. So difficult to sketch on this thing. Okay. Yeah. Okay. You can see your cover wants to rotate. Yeah. So when your cover tries to rotate, the only thing stopping the rotation is the bolts. Yeah. So you have 1, 2, 3, 4. 4 bolts stopping the rotation. So the bottom bolt obviously will be in compression, and then the top bolts will go into tension. Okay. Like that. Okay. So in this connection, the bolts will be subjected to both shear and tension. So you have to check for both. Okay. So these are cases where, so all these, everything on the right hand side, everything on the right hand side here, everything on the right here is shear and tension together. Everything on the left is purely shear. Everything on the right is shear and tension acting together. Okay. So you have to familiarize yourself. Okay. Okay. So now we get to the formulas. Okay. So the checks that you have to do. So if it's only shear, then you only check it for direct shear. Then it's the first table, it's the left-hand side row. Okay, if it's only shear, then there's only one formula for you to check for. If it's shear and tension, then you obviously have to check for shear and tension. 2 formulas to check. Now, there's also a case where you have shear and torsion. Okay, but this one, don't worry about it. We won't cover in our course. Shear and torsion, we will not cover in our course. So don't worry. You worry about shear together with shear and tension. Okay, torsion, we don't worry about it for this course. Okay. Okay. Now the formulas. Okay. Now the formulas. So these are all the formulas that you are going to use. Okay. So let's go through them one by one slowly. No, so for today's class, no example. Okay. I'm going to just go through formulas with you. Then after this, we go through examples. Maybe tomorrow after the test, or maybe next week, we go through the examples. Okay. Today, just go through the formula with you. All right. So bolted joints tension. So if it's just tension, that's the formula you use to check your bolt capacity. Now, obviously, before you check bolt capacity, you have to do analysis. You have to find out what are the forces in the bolts first. So there's another way of, so that's something I can only show you through example. I cannot give you formula here because different scenarios, you need to use different formulas. So to get the forces in the bolts, I cannot give you formulas for that. All right. All this, everything here that I'm showing you are the resistance, the formula for the resistance only. Okay. You have to compare this with the forces from your analysis later. All right. So these are only for the resistance of the bolts. Okay. So tension. So to check for tensile resistance in the bolt, that's the formula you use. K2 times FUB divided times AS divided by gamma M2. Now, everything's pretty straightforward here. There's nothing strange. AS is the area of the bolt. Simple area of the bolt. Gamma M2 is a partial safety factor, 1.25 given already. Yeah. FUB is the ultimate tensile strength of the bolt, which is, you go back to this table, FUB. If we use 8.8, we always use 8.8. So the FUB is always 800. Okay. FUB is always 800 because we always use 8.8 bolts only, grade 8.8 bolts. So FUB is always 800. All right. So back here. So there. So FUB is always 800. Okay. And the last but not least, K2. So K2 is 0.63 for countersunk bolts. Otherwise, you just use 0.9. Okay. So for normal bolts, is 0.9. But if you use countersunk bolt, then it's 0.63. So now you will ask me, what is countersunk bolt? Any guesses? What does it, when you hear the word countersunk, what does it mean? Okay. How many of you have helped your parents to assemble IKEA furniture before, or any furniture lah? Doesn't have to be IKEA. You buy furniture from the furniture shop. Sometimes it's not assembled. You bring it home, it comes in flat boxes. You have to take all the stuff out. You have to pasang the screw, pasang the bolts together for your furniture. Yeah. Some of you, I'm pretty sure lah, some of you have done it before. Okay. Assemble your own furniture. Okay. Now, when you assemble your furniture, sometimes they use screw, but sometimes they use bolts. Okay. The difference between screw and bolts is screw, you just screw it in one direction, and it grips onto the material. Bolt is different. As I explained earlier, bolt is the hole is already there. You put a bolt in from one end, and then you have to put a nut in from the other end. You tighten the nut. That is bolt. Okay, different from screw. Bolt is different from screw. Now, some furnitures, especially big furnitures, they use bolt. They don't use screw. Screw is not strong enough. They use bolt. Now, when you tighten the bolt, I'm pretty sure you have tightened countersunk bolt before. It's actually a bit difficult to tighten that countersunk bolt. So what is the difference? Countersunk bolt. So first of all, I just want to let you know. So K2 is for normal bolt. Okay. So K2 is for normal bolt. Sorry. K2 0.9. K2 0.9 is for normal bolt. K2 0.63 if you are using countersunk bolt. So now I will explain to you what is the difference between the two, countersunk and normal bolt. Where can I draw? Can I draw here? Okay. So you use bolt to connect two different. So you use bolts to connect two different plates together. So as I mentioned earlier, you put. Why does it keep doing that? Okay. So you put the bolt in through the hole, you tighten the nut, connection finish. This is normal bolt. Now, countersunk bolt is situation where you don't want the bolt to poke out. Okay, some furnitures, you notice, they do that. Okay, some furnitures, you notice they do that. The reason they do that is because, and then the hole here. Okay, the reason they do that is because then you can use your bolt. I'm going to use red color for the bolt. Use red color. Then you can put your bolt in there. Then you do the same thing. You put the bolt through the hole. You put the bolt through the hole, and then you tighten the nut. And then you tighten the nut. Okay. Yeah, you see the difference between the two? You see the difference between the two? One one, your bolt is exposed. The one at the bottom, your bolt is flush with the surface of the material. Have you seen the one the bottom one before? I'm pretty sure you have. Okay, so the one at the bottom is what's known as countersunk. Okay, countersunk bolt. Okay. Okay, have you seen it before? Countersunk bolt. Dah pernah kah? Yes or no?
Pernah, pernah.
Pernah kan? Yeah, yeah. If you assemble furniture, if you assemble enough furniture, you will see something like this before. Okay. Sometimes it's not very deep. Sometimes it's very shallow. But yeah, but they do this so that your bolt doesn't poke out and looks ugly. Okay. All right. So that's the difference between countersunk and normal bolt. All right. So if you use normal bolt, then K2 is 0.9. But if you use countersunk, then you have to reduce even further to 0.63. Okay. So you basically reduce your bolt resistance, the tensile resistance, if you use countersunk. Okay. Now, so that's for tension. Okay. Now, shear resistance, you follow the formula below. Okay. So shear resistance, you have AS. Okay, let's go through one by one. So shear resistance, you have AV. Now, AV is simple. You just look at the table below. As I said earlier, we only use grade 8.8 bolts. That means your AV is always 0. Your AV is always 0.6. Okay. I'm not going to try to draw this very difficult. Your AV is always 0.6 because we always use grade 8.8 bolts. So your AV is always 0.6. All right. FUB again, 800. Yeah. For grade 8.8 bolts, FUB is always 800. Gamma M2, 1.25, always 1.25. So the only thing that you don't know here is AS, is the tensile stress area of the bolt. Okay. So if this AS determines what bolt size you use. So this determines bolt size. Okay, this determines the bolt size. You choose a bolt size and then you put the area in. If the area is not enough, then you choose a bigger bolt or you put more bolts in. Okay, so it's simple as that. Okay. Okay. Now, this first formula is when the shear plane passes through the threaded portion of the bolt only. Okay. You can see it says here, this is the shear resistance for ordinary bolts where the shear plane passes through the threaded area portion of the bolt. If the shear plane passes through unthreaded portion of the bolt, you have to use this other formula here. Okay. Now, last, we have bearing. So bearing, you follow this formula. Most likely, we are not going to deal with bearing. Okay. But you study this on your own. In case we use it, then you need to know how to use it. But most probably, we don't worry about it. Okay. Now, one last important thing is this. The position of the hole. Now, obviously, when you design bolted connections, you have to make sure your bolt is not too close to each other. You cannot have one bolt right next to the other bolt. Then you don't have any steel in between anymore. You have to make sure there's enough space in between the bolts so that the plate so that the plate has enough area, okay, to sustain the loading. You cannot you cannot have two boards too close to each other. If the two boards are too close to each other, you cannot achieve full resistance. Okay, so the end distance and the spacing are all given in that table there. You have to make sure the bolts are not too close to the edges of the plate, and you have to also you've also got to make sure the bolts are not too close to each other. So those are the distances lah. So it's determined by D naught. D naught is the diameter of the bolt hole. So it's a multiplier. So it's a what? Multiplier of the whole diameter. Okay. All right. And this is the last slide. The last slide is for welded connection. Okay. So this one fairly simple as well. You read it on your own, but most probably we won't cover this. We will only cover bolted connections, shear and tension only. Okay. So this one, don't worry too much about it. But I've included it for your reference. And that's it for today. We will tackle the examples next week lah, probably. Okay. But before you leave, let me prepare the attendance for you. Okay. Change screen. Recently, they updated my tablet Android, the OS. So everything's a bit funny now. I'm not used to it. Okay, let me share the attendance with you. Okay, can you see